So first we start with randomness and being spontaneous. What is being random and spontaneous? So randomness is, simply put, the unpredictable behavior of the radioactive emission, right? So what is unpredictable? For example, if this is a radioactive source that we have, right, the direction in which these radioactive emissions will take place, and when I talk about radioactive emissions, I'm talking about alpha, beta and gamma, all three of them. It's possible that there is only one outcome, there is only one alpha, there is only one beta, there is only one gamma. It's very possible. So under all these circumstances, we're talking about all three radiations, depending upon the source, what type of radiation they may emit. So we're talking about all three. Okay, so the direction is unpredictable. We don't know if the radioactive source is left alone or in open. We don't know in what direction it's going to emit those radiations. So the direction is unpredictable. The second thing that is unpredictable is that if we zoom into the sample, let's say there are billions and trillions of atoms of those radioactive elements inside the sample. So if I zoom into the situation, for example, and let's say these are those atoms placed inside the sample, which atom precisely, or which particle precisely, is going to decay at a given moment and release alpha, beta and gamma radiation is not known. So that adds to the unpredictable behavior. That is why we call this randomness. Also, if we place a detector at random locations for this source, for example, let's move ahead with this one. Okay, so this is our radioactive source, and I place my GM tube in 4 different locations, and at random, of course, GM tubes at 4 different locations pointing towards the source. So we are expecting the radiations to come from the source towards these GM tubes. So, and of course, we are keeping the distance to be constant from all the directions, right? The readings observed on these GM tubes, our assumption or our idea before solving the question or before attempting this method was that they would be equal, or they should be roughly equal, but they are not. For example, this GM tube might give us a reading of, let's say, 4000. This GM tube might be giving us a reading of 3867. This might be giving us a reading of 4150. This might be giving us a reading of 3943, right? So all these radiation levels, or all these values on the GM tube are different. And even, not only this, even for the same distant GM tube, even for this GM tube, if I just wait for a bit, for this GM tube only, the readings of this GM tube are also fluctuating. They're also changing. So it's possible that it is, right now when I look at it, it's 4000. After some time I check it again, it's 4100. These are not going to be round values. I'm just taking round values for the sake of discussion. They are actually very random values, like this one, right? So it's possible in the next instant they are 3950. It's possible the next instant they are 3887 and something random. But one thing that will be predictable, or one thing that we can use or is workable out of this, is that if I do want to find out a steady value for the GM tube or for this radiation, what I'm going to do is I'm going to take the average of all these values, right? So I'm going to take the average of all these values, and then I'm going to find a stable value which I will use for my calculations. So the average is used for calculations of radioactive questions, right? So even at the same distances, the values of all GM tubes was not same. So that adds to the unpredictable behavior and randomness. Why do we call this random? Because it is unpredictable. We don't know what's going to happen. If a GM tube was placed at this location, keeping, let's say, in a circle, so what this GM tube reading will be, or what is the reading of this GM tube going to be, I can't even predict that. But what I can say is that it will be close to the average value, right? So all of these ideas add to the randomness of the radioactive reaction or the radioactive emission process, right? So we have that what direction they will emit radiation, we don't know that, so it's unknown. Which atom will decay exactly out of those 100,000 or a billion trillion atoms inside that sample? It is unknown. And whether the values that we're going to get from the GM tube, even at the same locations, will that be the same? No, it is unknown. So all of these things are unpredictable about the radioactive process. So we call this a random natured process. One more thing that what he does is he may ask you the question, what does changing values or the fluctuations, this is a key term that he sometimes uses, fluctuations, a simple English word that he uses to define or describe or to trick or at least to give you a hint that this is the behavior that he's actually referring to, right? So what does changing the values or fluctuations of the GM tube readings tell us about the nature? Again, nature will be a keyword for that question. Nature of the decay process or the emission process. So we simply write down the answer to this question would be simply that the radioactive emission is a random process. For 1 mark, and if the question is for 2 marks, then you add at least 1 point, that the direction of emission and the atom or which atom is going to decay. All of these things are unknown or unpredictable, right? So all of this discussion is for the randomness or the unpredictable behavior of the radioactive decay. Now we move towards the spontaneous nature of the process. We've done randomness, now we're going to move towards spontaneous. So simply put, if you look at the spontaneous nature, of the radioactive process emission, right? Spontaneous would mean that the process happens on its own. We don't start that. The process happens or starts on its own. Why does it start happening? Is because the radioactive nucleus is unstable. So an unstable nucleus decays to become more stable. That's why the radioactive emission takes place. And this reaction or this, you can say this decay process or this emission happens on its own. Nobody from the outside or no physical factor is trying to control this, or at least has the ability to control this. For example, what are we talking about spontaneous or being spontaneous? You see, this reaction is not affected by, or this emission is not affected by the following components. Temperature of the environment. What does that mean? It means that if I, let's say, have a sample of radioactive uranium, let's say 235, 92. I will be using this as a very common example, so I'm just referring to this one as right now. If we have a sample of uranium 235, right, and if I start heating it up, it is not going to start the radioactive process if it's not all happening already. And if it is emitting, let's say, some radiation, alpha, beta, or gamma, it's not going to increase the speed of those emissions. It's not going to make it happen more quickly. That's not how radioactive emission works. So temperature is a physical aspect of physics. It's not able, or it's not going to change the rate of emission. Second, if I add any chemical, for example, if I add a base, or if I add a basic solution, or if I add an acidic solution with a very low pH, right? So all of these things do happen in chemistry, that when you add strong chemicals, it does happen to do something, right? But not over here. Radioactive process, or the emission, of course, is not affected by simply addition of some chemicals, right? On the third account, we have pressure. Now, why do we see, or why do we have to say explicitly that pressure is not affecting it. You see, in chemical reactions or in physics or in some other aspects of chemistry especially, if you do apply some force on some chemicals, they do explode. For example, if you have ammonium nitrate, that is one of the elements that is used, or one of the chemicals that is used to light up the fireworks, right? Or to at least design crackers or firecrackers. It is very explosive in nature, right? So it does give out explosion, or it does give out that procedure or mechanism when a force is applied on it. For example, if you have some sample of ammonium nitrate and you apply a force with a hammer on it, it will explode, and it's a very dangerous experiment to be done, at least in laboratory. It has to be done in an open environment and with a trained professional. So we were expecting the same idea or same behavior with uranium or with at least radioactive elements, but they don't happen to do anything, or they don't happen to show any reaction or anything, even if some strong force or pressure is applied on them. So these factors do not affect the emission process of the radiation. Hence, we call this radioactive emission process as spontaneous as it is happening on its own. Why is it happening? Because an unstable nucleus is trying to become more stable. That's all it's trying to do. And to give you a simple perspective, how will you find out whether an element or for example an element of a periodic table is unstable or not? You see, that concept is not a part of your course, but I will just give you a small hint of it. You can research about this on your own. Generally, in physics, an unstable nucleus is found when the protons are more in number than neutrons inside the nucleus. If neutrons are more in number than protons, they generally form a stable nucleus. They generally form stable nuclei. But if protons are more in number, this is again our observation, and we of course have reasons for that why is it happening in this way. But if protons are more in number, then that element would most likely be a radioactive element, or would be most likely unstable. Okay, so now we're done with the spontaneous nature of the radioactive emission. Let's move ahead with the background radiation. That's a simple, smaller topic. Okay, so let's move with the background radiation. So what is background radiation? As the name suggests, background radiation is simply radiation coming from the environment, from the background, from, of course, the environment, of course. So why do we consider this, or why do we have to consider this? Because whenever we are conducting an experiment in laboratory or any other place, background radiation is always present. It's always going to be there, no matter what you do with it. And where is it actually coming from? You see, for example, if I have a radioactive element or a sample and it is enclosed in a lead container, this is how we show radioactive sources enclosed in a container. This is a lead encasing, and this is our radioactive source. And we use lead because we know that if lead can stop gamma radiation, it can successfully stop alpha and beta as well. So it's good enough for all of them. So to be on the safe side, we use lead because we are hoping, or sometimes we do know that this is alpha, beta or gamma, but if we don't know what that is and what the daughter particles are going to be, so we on the safe side just enclose it in lead so that we can be safe from all types of radiation. But when we do enclose this in a container, what that helps us to achieve is that all the radiation will now be expected to be emitted from just one direction. So it forms them into a beam. Previously in the randomness, what was happening that it was emitting radiation in all directions, which was adding to its unpredictable nature. So now what we're doing is we are enclosing it in a container so that all the radiation comes out just one point. So when we do place a GM tube meter in front of it, GM tube, it does give me the reading for it, but it also gives me one more reading. It also interferes, or it also intercepts another reading from the environment. That is the background radiation. Now where this background radiation is coming from? It's coming from the outer galaxies. We call them cosmic rays, and they are mostly gamma radiations. Why gamma? Because only gamma has the capability to pass through long distances. Alpha, beta have very small range, and they would quickly die out. So if I'm getting some radiation from another solar system or from another galaxy, that is in terms of gamma radiation. But since it has traveled a long distance, it does lose a bit of energy, so it's not harmful for us. So even if right now I'm sitting on the surface of the Earth, our bodies is still exposed to this background radiation, but since the value is so small, it's not fatal for us. And where do we expect them from? Different locations. It's radioactive waste. Now, since mankind has been using radioactive elements to make electrical energy, so whatever we are left with as the byproducts, we dump them directly into the ground on remote locations and enclose them into lead containers. So even that radiation is becoming a part of our atmosphere, right? Radioactive waste products, and then the new building materials. One interesting thing that we don't know as a common man is that the buildings that we create, for example, when we use the cement has one radioactive element as a constituent. We cannot make it without it. So when we do make buildings, when they are extremely fresh, when they're extremely new, the radioactive activity is at its peak. After approximately 40 to 50 days, the value reduces to such a low level because it is emitting radiation that it is now safe, or at least not harmful anymore for human consumption, at least be there. They have found alternatives to that. They have been working on that, but we do know that it is contributing to the background radiation. So all these elements coming from the earth crust due to radioactive waste, coming from the buildings that we're sitting in that have used cement in them, coming from the outer galaxies, all these elements are contributing to the background radiation. And the value that we generally expect, again, it's a general recommendation, is between 20 to 30. And the unit that we use for these values, the unit over here, of course, for even these values, the unit for the GM tube values is CPM. It is written as CPM, as counts per minute, right? So if it would not be wrong if I would write down CPM with all these values. It's simply as in this idea that when we go back to the GM tube, for example, if you remember, we had a counter installed over here, right? So this counter's value is actually being represented as CPM. So that's why we call this as counts per minute, as CPM, right? Okay, so coming back to this topic. Okay, so these are the values that we can expect from the background radiation, and we cannot emit them, we cannot reduce them, we cannot make them zero. You see, if from the outer galaxies those light rays or those gamma radiations can reach us, then what good a simple lead sheet is going to do? We can't stop them, right? So if, let's say, that the radiation value of my source only was 1000 CPM, and of course we're talking about an average value, otherwise the values that we may be getting due to randomness is 950, 970, 1020, 1050, and if we average it out, let's say that value sustains or comes down to 1000. So, but my GM tube shows me 1025. Why? Because something from the background radiation is also being experienced, right? Okay, so we were expecting the background radiation to be between 20 to 30. So the reading actually taken by the GM tube is 1025. So this reading is actually because of my source plus my background radiation. So this will not be the accurate reading. So what we are going to do is we are going to correct the count rate first. And how are we going to do that? We first measure the background radiation. Just a moment. So we are going to find the corrected count rate. And how are we going to do that? We are going to first measure the background radiation, and let's say it comes out as 25. Okay, fine. Then we measure with the source, and let's say it comes out as 1025. So the corrected count rate or the actual count rate would be 1025 minus 25, and the examiner will give you this value in the question for the background radiation so that you can at least find out what the source is worth. So my source is actually giving me 1000 CPM. So again, the problem is that we cannot stop the background radiation from coming in. It's always going to be there, right? So what we do is we measure all these values, right? We measure the background radiation, we measure the source. So then at the end of the process, we just subtract the background radiation and then move on with our reading, right? So this process is known as the corrected count rate. You will find this word in the syllabus. That's why I'm referring to that in the specific order, right? So these are the sources of background radiation. We must memorize them. And we must also remember this corrected count rate or the correct count rate method. Simply put, since background radiation is always going to be there, first we measure it without the source, then we measure it with the source, and then we just remove it. Similarly to the experiment that you do sometimes in grade 9 experiment of mass weight density, that first you measure the mass of the beaker, then we pour in some liquid, then measure the mass of liquid and the beaker, and then just to subtract the mass of the beaker to get the mass of the water only. So a similar analogy is being done over here, or similar ideas being implemented over here. So we're done with background radiation as well. Now we're going to move towards the deflection in electric fields. Tomorrow we will do deflection in magnetic fields and nuclear reactions. Today we will finish this at electric fields. Magnetic fields. For magnetic fields, please revise Fleming's left-hand rule before coming to that class. Okay, so now we have deflection in electric field, right? So the deflection in electric field, how we're going to do that? Let's say we have a positively charged plate. This is a positively charged plate. Why and how do we give this charge on the plates? We'll get to that later, let's say. And this is my negatively charged plate from simple static electricity chapter that we've done. Now I'm going to introduce all three radiations over here. So let's say we have introduced with the green beta, with orange we have gamma, and with the black line we have alpha. And the electric field and how actually we have connected them, be very careful about that. Sometimes he does ask you to draw the connections if you have to set up this experiment. So what we're going to do, we're going to connect this plate with a positively charged battery point or a battery terminal, and the other terminal will be connected with simply a negative terminal of the battery or of the cell, right? Okay, so let's understand and revise and try to remember that the charge on beta was negative as it was an electron. The charge on the gamma radiation is 0, there is no charge, and on the alpha the charge is positive, and the gamma radiation has no charge, so I'm going to represent it with 0. Although you don't need to do that, you don't need to show these charges, I'm just doing this for you. If this question comes in examination, you can just simply write down a line or draw a line representing alpha, beta or gamma, or simply labeling them with alpha, beta and gamma symbols, not writing down the positive, negative or 0 charge. You don't need to do that, but even if you do, it's not considered incorrect, but you don't need to do that. Let's analyze beta. You see, beta is negative and the upper plate is positive. So if they do happen to come into this contact, let's say this was its original path. I'm going to draw this with a dotted line. Let's say this is the beta's original path. If there was no electric field, this is where the beta should have been. But no, we found beta somewhere along this line. It was attracted towards the positive plate because opposite charges attract, right? You don't need to draw the dotted line as well. This is just for your reference and understanding. But since gamma has no charge, it would pass undeviated. It would not be attracted to the positive plate and it would not be attracted to the negative plate. Without any regards to any charge on the plates, it will pass straight through. So that is how we actually separate any type of radiation being received from any type of source. That is how we actually understand that whether this is giving us alpha, beta, or gamma, or what type of radiation is coming out of this. So we will have a detector of beta at this point, or we will have a detector of alpha at this point, and then we would just be waiting for all these radiations to be received. And at the very center we'll have a gamma detector, which is, of course, we can place a photographic film that we use for X-rays. Only gammas and X-rays can produce a pattern on them. That's a discussion for another time. But we do understand how the electric field pattern or the electric field is going to dictate the behavior of beta and gamma. I've mistakenly written as alpha. This is going to be gamma. Right? Now we move towards beta. Now there's going to be a slight difference between beta and alpha. You see, this should have been the alpha's original trajectory or original path. It should have went straight through if there were no electric fields, right? But this is not what's going to happen. So the alpha actually starts moving towards the negative plate, but notice one thing, that it has not bent itself as much as the beta has done that. So beta from its original position has deviated quite a lot. So I will write down high deflection. It has deflected a lot. But if I notice this for alpha, I see that in comparison to beta, it has deflected low. So I will say that this is low deflection. Now, examiner sometimes asks you, and this is exactly the diagram for a P1 question. The examiner sometimes asks you, why is that so? So the reason for difference in deflection are their own masses, is primarily inertia. You see, alpha is heavy and beta in comparison is very light. So it's easy for the electric field to move beta out of its original path than to move alpha from its original path. But alpha does end up moving towards the negative plate, but not as much as the beta. And we can see this in the diagram of electric fields as well. If I just try to zoom into this. Okay, so this is what we are looking at. You can see over here that alpha beam is being attracted towards the negative plate. Beta is being attracted towards the positive plate, right? And gamma passes straight through. And we can notice that alpha is being less deviated and beta is being deviated more. And again, this is all going to come down to the idea of inertia, and because the difference of masses, right? So what we have done so far is we've done deflection and magnetic field. This is what we have to do tomorrow, and nuclear reactions, right? That is all for today.